Okay, it's now time to start talking about homework 9. So I'll give a quick update on the class, right? This is homework 9. Homework 10 is applications of quantitative genetics, and that's it. And you guys are done. The week after that, I was supposed to be traveling, and therefore set the class as canceled for 2 weeks from now. Technically, I could still make those classes, but I'm not going to. So you will then have like a week off to catch up, to study, to do whatever you like during that week off. After that, we're going to come back for one more class where we do a paper reading, and then the final will be given. And it'll be just like the midterm. It'll be just like the midterm. I'll send it to you. You guys will mail it back to me whenever you feel like it. And if it gets to the point where the registrar is bugging me for your grade, I'll start bugging you for the exam. But until then, you will take as long as you like with it. And just be honest. Like, I mean, that was the other thing too. Like you guys did astonishingly well, but I had no reason to believe like any of you mistreated the exam. It all looked very fair. It all looked like, the mistakes you made were the sorts of mistakes everybody made when they make mistakes. You just got them right a whole lot of times. And it was just fabulous. Anyway, but you'll get the exam. You'll take as long as you need with it. You will send it back to me. And at some point, I'll tell you how you did if you're curious, or you'll just see your posted grade as A or possibly a B, but a whole lot of you heading towards A's. A whole lot of you are. What else was there to say here? I guess that's about it. You guys have any other sort of procedural, structural kind of questions? All right, we are on to homework 9. Linnea is going to start us off with problem 1, if she's on.
Hey, yep.
Yeah.
Okay, looks like you need to enable the screen sharing.
Again, I already did that once. That's interesting. Okay, yep. Try again. Very buggy today.
Okay. Oh, what? Okay, now this one. Okay. Yeah, you can see it. It should be a little previous file, I guess. Okay, so for this one, yeah. Sorry.
So talk us through it. I want you to talk us through it just so that everyone is totally on board, because we're going to do something like this 4,000 times. So do this.
Okay.
All the way up.
All right. So we've got our single diploid locus. We've got our genotypes, A1A1, A1A2, and A22. We have phenotypes that are corresponding to those genotypes. So just asking what is the mean phenotype, it's just taking the average as usual. So you have to sum the probability of getting that phenotype for every type of genotype. So in this case, we have what's the probability of getting 1, 1? Well, it's p squared because it's Hardy-Weinberg equilibrium. So we multiply that by y11. Same thing for the heterozygote frequency times y12, and then finally the T2 homozygote, and it's just the average.
That's it. Yep. It's just that. And to be perfectly honest, this is why we did homework 1 and 2 the way we did them. There is going to be this over and over and over, where you have done nothing more than apply the definition of an average. And you found the definition of an average by taking the frequency of a genotype times something. Here, we're just going to do a phenotype. In other problems, we'll do an effect. In other problems, we'll do one effect times another, but still finding expectations. Some of those expectations will correspond to variances, some of them to covariances, some of them to other things. But this all of quantitative genetics can be understood as an elementary application of the definition of expectation or maybe conditional expectation over and over and over and over again. And some of the problems are going to be so easy, there's just apply the formalism. Others are going to be a little bit harder, and it's going to be apply the formalism, but then it's going to take a little bit of algebra or insight to get down to a cleverish looking result. But questions about how we're starting? All right, up next with problem 2 is Michelle. Is she, no, Michelle I know is taking her qualifying exam? Yeah, Michelle's out, right, I think. So Young Xian for problem 2.
Okay. Sure. So in this question, we are going to get the mean phenotype mu x, and here I get the formula for getting expected phenotype, like expected normalized phenotype. So it's gonna be p squared x11 plus 2pq times x12 plus q squared x22. And this x11, x12, and x22 can be like written like this, like y11 minus mu y, and y12 minus mu y, and y22 minus mu y. And then I like cleaned up the formula and I got mu y minus mu y, which is 0.
Yep. That was the most straightforward application of the definition. If you had been feeling confident, you could have even said, in question 1, I have a random variable y. In question 2, I have a random variable x. X equals the random variable y minus the mean of y. So the expectation of x equals the expectation. You could just then write them all out, and you would have immediately seen, you would jump immediately to your last line of the expectation of y minus the expectation of y. But you have also now effectively proved it from first principles, and in either case, you need this. The mean, once for any phenotype on Earth, if you're going to do quantitative genetics, the first thing you're going to do is you're going to subtract the mean, the population mean of that phenotype, from everyone's observations, and then proceed. You're going to have a new phenotype that has mean 0. If you do that, you will be able to apply all your favorite quantitative genetics formula. If you do not do that, you'll be constantly fighting that mean. And it will be so much easier for you to think about your life with a phenotype that's centered at 0, so that everything can be thought of as a departure from 0 rather than an absolute value. And only at the very last step ever would you add back that mean to talk about the original variable rather than your transformed variable. Does this make sense? So Brooke, you want to do problem 3 for us?
Wow, it's like I knew it was coming.
Did you?
Yes, I do. Okay, 1 second. Okie dokie. Problem 3 was asking what's the mean phenotype for A1 and A2. So basically, the way I think I kind of intuited this a little bit, maybe there's a slightly better way to explain it, but basically alpha is the sum of the phenotype frequency given that that allele is frequent or is present over the allele frequency. So basically that is p squared times the frequency of A1 and then 2pq of x1, x2, the heterozygote, which is half. So you just knock that out, put that over p. And so basically I've done that kind of same format for A1, which basically knocks out p when you FOIL it out or break it down, so that you get alpha is actually equal to p times x11 and q times x12. And if you could use the same kind of logic and format, you end up finding the same thing for A2. Well, not the same thing, but a similar format for A2, where you have Q x22 plus B x12.
Yeah. So you have intuited your Bayes result entirely correctly. What you wanted was the probability of picking an A1, given that you picked an individual who had an A1 allele. And you wrote down that as the probability of picking an A1 individual, p squared, times 1. That is the probability of picking an A11 individual, given that you picked an A1 allele, divided by the probability of picking. Here, I'll actually show it to you out in I sort of, whoa, continue. So you absolutely, now I'm on the exam again. Boy, let's see if I can get this right at all today. Screen share. That's not fun. Let's try this. Now, screen share. Are we on my answers?
Yes.
Good. So you correctly intuited the probability of picking an A1 individual, given you picked an A1 allele, is the frequency of A1 individuals, the probability you picked an A1 individual, times 1, plus this is the probability of picking A1 genotype and an A1 allele. This is the probability of picking an A1 individual and an A1 allele. So the probability of picking a A1 allele overall is P. So the probability of picking an A1 individual, given you picked an A1 allele, is this thing divided by the and probability. And so it's just really P. The probability that you picked an A1 individual, given that an A1 was picked, is Q. And the probability that you picked an A2 individual, given an A1 allele, is picked, is 0, which gets us to your exact formula. That alpha 1 is P x11 plus Q x12. By the exact same logic, the probability of picking a heterozygote given an A2 allele was picked is P. The probability of picking a homozygote given an A2 allele is picked is Q. So the average phenotype of an individual with an A2 allele is PX11 plus QX12. That is the formal definition of alpha 1 and alpha 2. That's what we're going to use throughout the rest of quantitative genetics. That's what alpha 1 is. It's the mean phenotype of an individual with an A1 allele. Alpha 2 is the mean phenotype of an individual with an A2 allele. We will find out that we can write the mean phenotype of individuals with certain genotypes as very simple functions of alpha 1 and alpha 2. We will, in fact, find out that we can write down the covariance between related individuals as relatively simple functions of A1 and A2, of alpha 1 and alpha 2. But before we get there, we as a class now have the firmest possible definition of what is meant by an additive effect. It is the mean phenotype of an individual with that allele. The additive effect of an allele is the average phenotype over all humans of people that have that allele, or of all organisms in this population that have that allele, weighted by the sort of frequency with which they have the allele. That should be, sort of in the forefront of your mind, that's what an additive effect is. It's just the average phenotype, conditional that you have the allele. And once we know what the average phenotype is, conditional that you have that allele, we'll be able to do lots and lots and lots of other things. We will be at some point calling this the additive effect of the allele. But we'll get there soon. At this point, does anyone have any questions? All right, Xiaoji with problem 4.
Okay, problem 4.
Yeah.
I'm not looking. Okay. So problem 4 is, if we have a locus that is additive, then the phenotype of A1, A2 is in between the two homozygotes, so that X12 equals X11 plus X22 divided by 2. Show that PX11 plus QX22 equals 0 for an additive locus. So on my first line, I wrote that 0 equals 0 is the mean phenotype, is the mean, I guess, normalized phenotype. And we can make a substitution for X12. So that becomes just P squared X11 plus PQ X11 plus X22 plus Q squared X22. And then we can regroup some terms so that we end up with X11 times P plus Q. Since P plus Q equals 1, we just end up with X11 times P. And then we also regroup the terms for X22 so that we end up with X22 times Q times P plus Q. And in the end, we end up with X22 times Q. So X11 times P plus X22 times Q equals 0 as what we started with.
Perfect. And we're going to do that because we're going to use this once or twice over the rest of the homework. But also to warm us up for several of the tricks we saw in here, where in the first step, all we did is substitute in, and at some point or another, we group terms and often found P plus Q is equal to 1 or something very similar to that. Any questions about this? Anyone have any alternate proofs they wanted to show? This is the simplest and the easiest. And it was really sort of the first warm up of these proofs. Mega, do you want to try problem 5?
Yes. Okay, so for 5, we're just proving these 3. And so x11 equals 2 alpha 1, and I just plugged in the value we found from 3, I believe, or 2, or problem 4 maybe. And then I just expanded it out and canceled terms. And then here I added in I substituted for x12 and solved down, canceled things out again. And I got x11. And then I did the same thing down here and the same down here.
That is the right idea. Just leave this up for now. Does anyone have any questions about this particular sort of proof derivation? Let's talk about this now. So in the first problem, or in the problem 1 or 2 ago, we defined alpha 1 as the mean phenotype of a individual that has an A1 allele. Pick an allele if it's A1, the mean phenotype of the person it came from is alpha 1. Pick an allele if it's A2, the mean phenotype of the person it came from is alpha 2. It also turns out the mean phenotype of an A1 individual is 2 alpha 1. The mean phenotype of an A2 individual is alpha 1 plus alpha 2. And the mean phenotype of an A2 individual is 2 alpha 2. If the heterozygote has phenotype halfway in between the two homozygotes. So if the locus is additive, the phenotype of the mean phenotype of the three genotypes is 2 alpha 1, 2 alpha 2, and alpha 1 plus alpha 2. So for an additive locus, the phenotype of the genotype is just given by adding the alphas together. If you have two A1 alleles, take one A1 allele, one alpha, and add it to another alpha. If you have one A1 and one A2, add an alpha 1 to an alpha 2. If you have two A2 alleles, add two alpha 2s together. Thus, for an additive locus, alpha is very much the effect of individual alleles on the genotype. It is not only the sort of weirdest conditional mean on the population, it is also the additive effect of a single allele if the locus is additive. And in fact, the means of the genotypes can be found by doing nothing more than adding together the appropriate alphas. So all that makes sense. We're going to keep building from here. Make sure you're on board.
I have a
Okay.
question.
Up, question?
Yes. So for part of 5, we're proving that P alpha 1 plus Q alpha 2 is 0.
Oh, do we
Um,
do that proof?
Yeah, I actually forgot to write it down too for this problem.
Oh, it was scrolled down. It's down here.
So on Thursday, you had mentioned that holds globally. So
Yeah.
for any locus with any kind of dominance relationship,
Yep. Let
for
me,
the subsequent problems, I used that property, and I was just wondering if we were
Well, yeah.
supposed to.
yeah, absolutely.
Okay.
Yeah, and let me share my screen because I forgot that was part of the problem. Because, can you see mine now?
Yes.
So for my problem, I start with P alpha 1 plus Q alpha 2, and then take PX11. So the definition of alpha 1 is PX11 plus QX12. The definition of alpha 2 is PX12 plus QX22. Nothing about this assumes additivity. This is just the definition. P times alpha 1's definition plus Q times alpha 2's definition gives me P squared X11 plus PQ X12 plus PQ X22 plus Q squared X22. There's probably some weirdness there, which is P squared X11, 2PQ X12, Q squared X22. That's 0 from problem 2. So nothing about this derivation used the additivity property. So this relationship, P alpha 1 plus Q alpha 2 equals 0, is a fact of any locus with mean 0. And yes, that is something to use often under additive and non-additive loci. It is just a fact. Does that make sense to everybody? That we proved it here using nothing about additivity. And it is absolutely just true regardless. And that's even like a quick way of finding it. If you knew the alpha 1 effect and you know the frequency of the A1 allele, you can find the frequency of the effect alpha 2 instantly in your head by saying alpha 2 equals P alpha 1 divided by Q. And in fact, you will struggle to find, well, if you just get yourself in the simulation business, you'll struggle to make coherent simulations without using this effect. Or rather, you'll struggle to your simulation won't have the amount of additive variance you think it does unless you use this, is probably the best way to put that. You'll probably mess it up somehow. At least you will if you're me. But anyway, that is true always. Or at least for any normalized locus. Hey, Taylor, you're up next with the next problem, whatever that is.
Okay, so problem 6, we're considering a locus with any dominance relationship. We can think of x1 plus, it should be x11 equals 2 alpha plus d11, x12 equals alpha 1 plus alpha 2 plus d12, and x22 equals 2 alpha 2 plus d22. So we're thinking of this d term as your general dominance deviation. And we're not trying to find the expected value of this. So we just use the definition of expectation again. Instead of leaving it in terms of the dij's, I substituted in the corresponding phenotype minus the additive effects. And then it's just some algebraic manipulations pretty much. Yeah, you end up getting -2 times what we just proved in problem 5 to be 0. So our expectation is 0.
Yeah. That's it. Now, okay. Just algebra. You started with, again, definition of expectation, frequency times the value corresponding to the frequency, substituted in the definition of that, did some rearranging, found some p's plus q's, made them equal to 1, multiplied by -1s as necessary, and ended up with alpha 1 times p plus alpha 2 times q, which was shown in the previous problem to be 0. So, what did we just learn? Now we're really moving on quantitative genetics. For any additive locus, we know the phenotype of the genotype can be written as the alpha 1 plus alpha 1 for an A1 individual, alpha 1 plus alpha 2 for a het, alpha 2 plus alpha 2 for the other homozygote. That's true for any additive locus. And for any locus that isn't additive, surely we can write its phenotype as the additive phenotype plus something, the other additive phenotype plus something else. The last genotype is the additive amount plus something else. I'm not going to tell you what those values are, and we don't know anything about them right now, but I do already know that their mean is 0. That's useful, neat in some fashion or another. That, again, when you normalize a locus to have a mean of 0, you can think of the mean effect of each genotype as the sum of the additive effects plus some deviation whose mean is 0 across all of your 3 different genotypes. This is some other little deviation-ish term who has mean 0. And we're going to call this, for now and ever, the dominance deviation, because it is the difference between the phenotype, the observed phenotype and the predicted phenotype if the locus were additive. For an additive locus, we know the phenotype is going to be just the alphas. For any other locus, the phenotype will be the alphas, potentially plus something. And that potential plus thing we're going to call a dominance deviation. And it's the amount that genotype average of that genotype's phenotype differs from what it would have been had the locus been additive. Is this all clear? So to quantitative geneticists, the word dominance means deviation from additivity. Any deviation from additivity, any way in which the heterozygote is anything other than halfway in between the 2 homozygotes, is considered some form of dominance. And it results in the genotypes not being simply their additive phenotype, but the additive phenotype plus a little bit of something. And that little bit we're going to call the dominance deviation. These all clear. And in a slight, sort of in a slightly variant way from the way a pure population geneticist thinks of the word dominance. We talked about H being the dominance coefficient and how H gives us dominance by doing something to the heterozygote. To a quantitative geneticist thinks about dominance as affecting all three genotypes, not just the heterozygote. Dominance is the effect on all three of the genotypes from what they would have been had this been an additive locus. So you can't describe dominance to a quantitative geneticist with a single term necessarily. Well, maybe you can. Maybe you can do it as a variance. But you can't, on the additive scale, you sort of need all three of them, or at least you need two of them, because they're going to sum to zero. And so dominance to the quantitative geneticist is the deviation in each phenotype from its expectation under additivity. And the dominance variance is going to look like that thing summed in some fashion. Well, you know what it is already. Questions? Jim, you're up with problem 7.
All right. So I never really got the trick of, P plus Q equals 1 to pull that out and solve everything. So I don't really have the algebra.
Okay.
But I think I have the spirit of the idea of the question,
Yeah.
which was to ask, find expectation of A, D, and the variance of those things.
Yeah.
So I basically just knew that these two had to be 0 from our discussions.
Yep.
But now we've kind of shown it above, right? These things go to 0 by pulling out the P plus Q.
That's the trick.
And then the variance is similar, but here you're using kind of the formula where it's the expectation of the thing squared minus the quantity expectation squared. And so if we know the expectation is 0, that's this part here that gets subtracted. But all we really care about is that first part. So it's the same as the expectation, but the things are squared inside. And I don't know how to simplify that further.
So the first thing to say is there's something crucially wrong on your page. The additive variance is the sum, not the difference of P alpha squared and Q alpha. You have P alpha 1 squared on what I see as a minus sign, where this needs to be a plus for P alpha 1 squared plus Q alpha 2 squared.
Oh, down here?
Yeah.
Yeah.
That is a plus sign.
I probably just got that from the textbook somewhere. I was trying to figure out what I was supposed to get to.
Yeah, no, that's exactly right. It's just you've written it down without a key plus sign there. And let me show you sort of my painful or not so painful derivations of this. Let's share screen. And again, it is exactly how Jim set them up with a bit of algebra in between. So, problem 7. Are you guys seeing my screen? The expectation of the additive effect. P squared times 2 alpha 1 plus 2pq plus alpha 1 alpha 2 plus q squared times 2 alpha 2. Write that down. Pull out a p plus a q, pull out a p plus a q, and you get 2 p times alpha 1 plus q times alpha 2, which was 0. The variance in alpha, which we're going to start writing as VA, is equal to the expectation of A squared minus the expectation of A, quantity squared. Up here I showed you that was 0. So it's just the expectation of A squared. P squared, 2 alpha 2 squared, plus 2pq, alpha 1 plus alpha 2 squared, plus q squared, 2 alpha 2 squared. Foil some of this crap out. Now I've collected terms in alpha 1, where I've pulled out a 2p alpha 1 from that. I've pulled out a 2p alpha 1 from that. I've pulled out a 2p alpha 1 from this, and gotten something like that and something like this. Did a little more rearrangement. I turned my 2p alpha 1 into a p alpha 1 and a p alpha 1. So I got a P alpha 1 plus Q alpha 1 plus P alpha 1 Q alpha 2. One of those numbers is 0. The other is alpha 1 times P plus Q. That's supposed to be P plus Q. And that's a 2 alpha 2, and I pull that out. And that should have been a Q there rather than a 2. And I got 2P alpha 1 squared plus Q alpha 2 squared. It is algebra all the way down. For the variance and dominance, I've probably told you guys don't even try. Again, just from the definition, it's equal to the expectation of D squared minus the expectation of D quantity squared, which is just the expectation of D squared, which I'm going to write in this form to start with. You can play with this for hours and get lots of really interesting looking things, but I've never found anything any easier to remember or use than just the definition. Maybe one of you will find something that is neater than the definition, but I've never ever found anything that is really any easier to use than just the definition. But there it is. The mean effect of the mean dominance deviation is 0. The mean additive effect is 0. The variance is just the additive variance squared plus the other additive variance squared times the frequency with which an allele is this thing plus a frequency with which the allele is that thing times 2 because your diploid organism is made up of 2 alleles. If you had had a haploid, we would have gotten the additive variance was P alpha squared plus Q alpha squared. Interestingly. Here, because it's a diploid, we get a 2 out front. So the additive variance is the number of alleles times the probability of pulling an A1 allele, P, times its effect squared, plus the probability of pulling an A2 allele, Q, times its effect squared. If this had been a multi-allelic system, we would have gotten the frequency of the A1 allele times its effect squared, plus the frequency of the A2 allele times its effect squared, plus the frequency of the A3 allele times its effect squared, ... The additive variance is just the frequency of the allele times its effect squared, summed over all alleles. If your organism is a diploid, you got a 2 in front. If your organism is a triploid, you'll end up with a 3. All you plant people are weird. Anyway, that's additive variance. This is dominance variance. It's just the deviation from additivity squared, summed over the frequency of all the genotypes. That's what dominance variance means. Take the additive variance, which we have well defined, take the actual phenotype, subtract what it would have been were it additive, square that value, sum over all genotypes weighted by the genotype frequency. You have the dominance variance. This should be in your head the rest of your life. That's what dominance variance means. It's the difference between what I would have had were this a purely additive locus, that in what I actually got, that difference squared, summed over all genotypes, weighted by the frequency. There's nothing mysterious about dominance variance. It just is defined this way, and you now know it all. Questions?
Yeah, I think just to kind of tie it all together. So both additive and dominance variance are related to the genetic components. So I think I'm just trying to wrap my brain around. So the dominance, or I guess maybe what's the better way to define additive again?
Additive is what the phenotypes would have been if the heterozygote had phenotype exactly halfway in between the
Okay,
two homozygotes.
perfect. Yeah, thank you.
So if the locus is additive, if the heterozygote has phenotype halfway in between the two homozygotes, that's all there is. There is nothing going on here other than additive variance. There shall be no dominance. Only in the case where the heterozygote isn't halfway in between will there be dominance variance. And that dominance variance is the difference between the variance that it should have been had it been additive and what you in the variance it actually is. It is the increase in variance due to a deviation from additivity. Questions? Okay, Chris, you want to take a shot at the next problem? Did you tell me you didn't get there? I can't remember.
What? Sorry, we're on 8, is it?
Yeah, I
okay.
did.
All right.
Yeah, I'm sorry if several of you have written to me this week and said you're in the middle of your qualifying exams and this homework is coming in late. If you are one of those people and I have already forgotten, I am sorry for having already forgotten, but no worries. We perfectly well understand.
All right. So so question 8 asks us to show that the covariance of A and D equals 0. So we know that the covariance of 2 terms equals the expectation of first term times the second term minus the expectation of the first term times the expectation of the second term.
Yeah.
And that essentially.
That is true if they're independent. How do you know they're independent?
Well, let's see. So
is it obvious to you? It's way not obvious to me. It's like a million times not obvious to me that they're independent. Maybe you've got an insight here.
I don't know that I do.
Yeah, I know how to prove this very, very formally, but I have no insight that they ought to be independent.
Okay.
Does anybody have this proof that would like to show it? It is I think the hardest single proof in this homework. Does anyone want to give it a shot?
I can make an attempt. Okay. Share screen. Perfect. Is it up now?
Yep.
Awesome. So I have the same setup. The covariance of A and D is the expected value of A times D plus the expected value of A times the expected value of D. We showed in the prior problem that both of these are 0. And so we're left just solving the expected value of AD. I plugged in the A values, so 2 alpha 1, alpha 1, alpha 2, 2 alpha 2. I plugged in the DIJ, D11, D12, D22, and then I wrote the DIJs in terms of the XIJ and the additive variance. So for example, here D11 became X11 minus 2 alpha 1. So I went ahead and I plugged everything in, and then I expanded. Yep. So I expanded again, and so now I have all of the terms. Essentially, I believe what I did was, in some cases, like for example, I changed, it seems like I put alpha 1 back in. So where I had alpha 1, I ended up with putting px11 plus qx12 for alpha 1, and here px12 plus qx22 for alpha 2. And that is
I think all you did actually is you just collected terms, right? You pulled P alpha 1 out of this thing,
Oh, you're right.
a P alpha 1 out of that thing. You pulled a 2Q alpha 2 out of that thing, a 2Q alpha 2 out of that thing. And then I think you rewrote the bottom thing in some fashion or another. And then you noticed that was alpha 1, or hopefully you noticed that was alpha 1. And you noticed this was alpha 2, which makes 2P alpha 1, 2Q alpha 2. And then we still have that minus shit to deal with, which it looks like you've done a similar thing to by pulling out a P squared plus PQ alpha 1, Q squared plus PQ alpha 2. That's P alpha 1 squared. That's 2 alpha. And you got 2 VA minus 2 VA, or rather VA minus VA.
Sorry, it was kind of a miracle.
Yeah. It's
But
not a miracle.
essentially, you gave me this very helpful hint that I'm supposed to get something that looks like VA minus VA. And so knowing that I kept that in mind from the beginning and tried to get two things that look like VA, but this is how I did it.
I think there's maybe let me share my screen. There's possibly I'm not sure it's any neater than yours, to be honest with you. But can you guys see my screen? So Kiana and I have exactly the same setup up to line 3. And in line 4, I think this is probably the same setup too. I made sure I have all the positive terms on one side and all the negative terms on the other side. And all I've done from the positive terms is I pulled out a 2P alpha 1, and this is what was left over, and a 2Q alpha 2, that was left over. And if you look at the negative terms were P squared 2 alpha 1 squared plus 2PQ alpha 1 plus alpha 2 squared plus Q squared 2 alpha 2 squared. This is immediately VA, whereas the positive terms I had a little more work to do. When I pulled out the 2P alpha 1, I got PX11 plus QX12, which is the definition of alpha 1. When I pulled out when I pulled out the 2Q alpha 2, I got PX12 plus QX22. That's the definition of alpha 2. So I got 2P alpha 1 squared plus 2Q alpha 2 squared minus VA, or VA minus VA. There may be other ways of doing this proof, but I don't know them. And so, Chris, getting back to your intuition, there is something going on here, that the covariance of A and D end up looking like the variance of A minus the variance of A. So if there's a geometrist among us, you can probably see I've done something to set this up to make D look like an orthogonal projection of A. And so that the variance of 1 looks like the covariance between them looks like just the variance of 1 with the sign changed. I mean, there's something very, very deep going on here that maybe lets people with better intuition than me immediately understand why the covariance is 0 and know that the covariance is going to turn out to be just one of the variances minus the other. But I don't have that kind of intuition, and I can't get there without this miserable little proof. And it's just a miserable little proof. But now that we are there, boys and girls, this is now like again, a little bit of something interesting. The additive and dominance components have no covariance between them. Even though they are defined based on each other in these kind of weirdy, wobbly, intertwined ways, they are independent in some level. At least their covariance is 0. So they have been defined orthogonally to each other in some manner. That the the additive variance and the dominance variance can be thought of in a practical sense within a locus as independent of each other. And therefore, if you knew the additive variance, it doesn't tell you anything about the dominance and vice versa necessarily. And that's something to have in mind too, that because the additive and dominance variance within a locus are independent of each other, we really do think of these variance components as separable. And we will be thinking about the total genetic variance as the additive variance, particularly at an individual locus, as the additive variance plus the dominance variance. And we don't need to imagine that they're somehow correlated or there's some covariance here that we're missing. They are uncorrelated. They have zero covariance as they are defined. Up next is Kevin with the next problem.
And that we're at 9, correct? So
I think so, somewhere in that range.
yeah. So for this one, it's kind of on the half of the screen.
Yes.
So for this one, it asks to find the expected value or expected value of P. So I just used the kind of additive property of the expected values, and we already defined that expected value of E is 0. We already know that expected value of A is 0. Expected value D is 0, so that's just 0. Yeah, and then you also asked for the variance of P, which we'll call VP, going later on. So I found the variance of all this added up. I know that the covariance of AD is equals 0, and so I have the variance of A, which we call VA, variance of D, it looks kind of like a cube, the variance of E, and then added to the 2 covariance of A, E plus covariance of DE.
That's it. That's it. So for a single, if all there were is a single locus, the variance in the phenotype, variance of the population can be thought of as the additive variance of the locus plus the dominance variance of the locus, plus twice the covariance between the additive and environmental terms, plus twice the covariance between the dominance and the environmental terms, plus the environmental variance. Or VA plus VD plus VE plus a few covariances. Does this all make sense? This is just from the definition of variance. Nothing, this is a one-line proof. You could have done this first day. And in fact, you did do this first day for some weirdo versions of this in some fashion. And but that's what people are talking about now. For the rest of your life, when people, I mean, we'll complicate it by adding more loci, adding more covariance terms. But those look just a little bit like annoying details. The heart is right here. You pick a human, you pick an organism, you pick your favorite organism. Whatever you're measuring, you subtract out the population mean. That organism now has mean 0. There is some variance in the population that just, the whole sort of, there's a distribution. All organisms, some of them are at the mean, some of them are away from the mean. The variance in those organisms, the whole population variation, can be thought of as nothing more than the additive variance of our locus, plus the dominance variance of our locus, plus some covariances that we don't much think about, plus the environmental variance. These are kind of deep ideas, but they're also really painfully simple too. There's both too little and too much going on. Like there seems like there's a lot going on here, but there's really very little so far. And we're not going to embarrass anybody by doing problem 10, which just says if all those covariances are assumed to be 0, then the variance in the population is equal to the additive variance plus the dominance variance plus the environmental variance. And these things are really sort of fully separable and can be thought of as kind of independent and additive. Questions? Julie, you're up with problem 11, which is a
Sure.
problem I won't do.
So there are 9 possibilities, and then for each line, the probability is calculated. First, the probability of the first person being an A1, which is P squared. And then the second person is A1, given that the first person is an A1. So if they have shared 0 alleles identical by descent, then it has to, it can only has P squared, so randomly picked alleles. And then if they share 1 allele, then since this person is A1, so one of this allele will be A1, and then the other one has probability of P being an A1 allele. And then if they share 2 alleles in this scenario, it is perfect. But then in this scenario, it's impossible. So there's no R2 here. And then you just calculate these for every line. I won't go over all of those.
That's it. Does this make sense? So what Julie wrote down is the probability the first person was A1, P squared, P squared, P squared. First person was A1, A2, 2PQ, 2PQ, 2PQ. First person was A2, A2. Q squared, Q squared, Q squared. These are the phenotypes, whatever. The probability that you get an A1 genotype with an A1 genotype is the probability they're unrelated, which is just P squared. The probability they share 2 alleles in common, which would be the probability 1. They have to have the same genotype if they share 2 alleles in common. Plus the probability they share 1 allele in common. Which allele is it? Oh, it's going to be an A1 allele for sure. So they share an A1 allele, and the probability the other allele is an A1 is P. For the next one, probably the first guy's A1 is P squared. If they share 0 alleles in common, the probability the second person is A1, A2 is 2PQ. If they share 1 allele in common, what is that allele? Oh, it's got to be an A1 allele. So the probability the second allele, the unshared allele in this person is an A2, is Q. So it's R1 times Q. And if they share 2 alleles in common, well, that's not possible, as Julie said. For the next one, it's P squared. The probability the first genotype is A1. The probability the second genotype is A2. Well, they can't share 1 allele. They can't share 2 alleles. It's only possible if they are unrelated to each other, in which case it's Q squared. 2PQ for the first guy. If they share 0 alleles in common, the probability of the next one being A1 is P squared. If they share 1 allele in common, we actually start having to write down, she has simplified a lot here. If they share 1 allele in common, with probability 1/2, it's the A1 allele. And this person is A1 with probability P. With probability 1/2, it's the A2 allele. And this, well, that's not possible. And that's what you end up with here. With A1, A2, you're going to end up with a lot of possibilities with the 1 allele. If they share 1 allele and it's A1, with that happens probability 1/2, and the other allele is 1 with the Q. If it's the A2 allele, the other one's an A1 with probability P, and so you guys get it, I think, at this point. You have to iterate over all the possible alleles they could share, and then the probability that the missing alleles are picked at random, which is just their population frequencies. I assigned you this problem because I want you to get used to thinking of R0 as the probability two individuals share 0 alleles. R1 is the probability two individuals share 1 allele. R2 is the probability two individuals share 2 alleles. Gillespie wanted you to do this problem so you could calculate covariances. I don't want you to use this to calculate. I mean, you can. If it's easier for you to, you can use this table to calculate covariances. But we're going to try to understand them rather than rote force this goddamn table. But it is important that you onboard R0, R1, and R2. R0 is the probability these two individuals share 0 alleles IBD. R1 is the probability they share 1 allele. R2 is the probability they share 2 alleles. This hopefully will become intuitive that if they share 1 allele, they can share additive effects. If they share 2 alleles, they can share both additive and dominance effects. So when you're looking for correlations between individuals, we will find that they are functions of R1 and additive effects and R2 and additive and dominance effects. And we're going to write a number that is 1/2 R1 plus R2, and we're going to call that R all by itself. That R all by itself is the coefficient of relatedness by some people's definition, and it is the fraction of the genome the individuals share. It is the probability that they share 2 alleles times 1 plus the probability they share 1 allele times 1/2. It is the fraction of the genome shared between individuals. R equals R1/2 plus R2. And we will simplify, although everything we will derive about the covariance between individuals will be a function of R1 and R2, we will often see things that look like R2 plus R1/2, which we will simplify and just group and call the letter R the coefficient of relatedness. Is this table, where it came from and what we're doing in it, clear to everybody?
I'm actually still just a little bit confused about, like, I was trying to understand it from the text too, but I'm a little confused why something like R0 and R2 show up in, say, like term number 1, where you have your 2 genotypes, which are A1A1 and A1A1. Because I could follow the table and I could look at the table and the reference, but the logic behind it doesn't really make sense to me, because it feels like those shouldn't.
Yeah, let's do it again. Yep. So what we want is the probability of an A1A1 genotype and an A1A1 genotype. So that is the probability of an A1A1 genotype given the first person is an A1A1 genotype times the probability that the first person is an A1A1 genotype. So I wrote this as the probability the first person is an A1A1 genotype. And now I'm going to write down the probability the second person is an A1A1 genotype, given that the first person was an A1A1 genotype. And I'm going to write that down as a function of how related the two people are. So the probability the first person is A1A1, the probability the second person is A1A1 as a function of how related they are. They are related as they either share 0, or they share 1, or they share 2 alleles. Nothing else is possible at this locus. So the probability they share 0 alleles is R0. If they share 0 alleles, what's the probability A1, the second person is A1A1? Well, they share 0 alleles. So this is just a random draw from the population. The chance that they're A1A1 is p squared. If they share 2 alleles, well, the first person is A1A1 and they share 2 alleles. Therefore, the second person must be A1A1. There is no other possibility. So if they share two alleles, the probability the second person is A1A1 is the number 1. So we've multiplied R2 by the number 1.
Okay.
If they shared one allele, well, we have to actually sum over all the different things. They could share one allele and it could be an A1. Or they could share one allele and it could be, okay. The only way they can share one allele is if they share an A1 allele, because this person only has one type of allele. So if they share one allele, it is an A1 allele. What is the probability the second allele is A1? That's just a random draw from the population with frequency P. So the probability the first person is A1 is P squared. The probability the second person is A1 is the probability they share two alleles times 1, plus the probability they shared no alleles times the Hardy-Weinberg frequency, plus the probability they share one allele, which means they shared an A1 and then got an extra A1 by chance, which is probability P. Does that help?
Yeah, I think so. Thanks.
I actually, I don't know if this is neat or not, but I was a bit confused by this too. But when I like drew it out with a picture, it like helped me a lot. So I could share that if
Show
anyone
your
wants to
picture
see it.
then, please. Because I do this with nothing other than these horrifying conditional probability problems, and they're no fun for anybody. So if there's a clean, intuitive picture, that would be gorgeous. Oh my God.
I mean, it makes sense, but like
No.
until you like see it, you don't. Yeah. I think it's just what you were saying, but for me, it helped to like visualize, like there's a difference between the individual sharing, they both have an A1 and that A1 actually being identical by descent. So like, for instance, if you have two A1 alleles, these like pink alleles, the individual you're interacting with, they could still have A1, but they might not be IBD. So there's three things that could happen is there's none that they share, which is R naught. And then you multiply that just by what's the chance of them having A1 period, P squared. Or you could share one IBD, which is the R1. Then what's the probability they have another A1 just by chance is going to be P. And then what's the probability you both share it is going to be just that R2. For me, I got a little bit confused with A1, A2, where you had to figure out, there was this 1/2 term, but you just explained it a minute ago, which is just that there's R1 chance that they share one, but then you also have to say, well, it has two alleles, so there's a 1/2 chance that you were talking about the first allele, I guess.
Yeah, there may be more boxes there you need, effectively, whether they're sharing the first allele or they're sharing the second allele in your graphical. We need to be more explicit to quite get it fully right. But yeah, that's great. Yeah. Why do we do this? Well, again, I told you I wanted you to do it mostly so you get very used to the definition of R0, R1, and R2. But in a very, well, maybe it'll be next time, but very soon, we're going to start writing down the covariance between individuals, which is going to be written in terms of these R0, R1, and R2 terms together with, with effects of some sort. Let's Kiana, as the last thing we do in the class today, do both of the two stupid proofs about covariance and variance and sums of covariances, just to get those out of the way. And then we will stop there for today.
Okay, sounds good. Share screen. I'm sorry, I have like 100 things open. Okay.
Cool. That too.
So the covariance of a random variable in itself, I just decomposed it using the covariance of x and x, the expectation of x times x minus the expectation of x times the expectation of x. It simplifies to just the variance of x based on this expansion. For problem 13, this was cool. I didn't know that math did this, but essentially I expanded this covariance of these two sums into a similar kind of expectation format. And then I multiplied the inside here out, and I assumed that based on the rules of expectation, I could separate these into individual expectations. And then over here, I also essentially just FOILed. After arranging the terms together, you see that you basically have 4 individual covariance terms. And that's all I did.
Yep. For any sum, you can write them as the sums of the pieces of the covariances. That, yes. I'm not sure anybody knows that until you encounter it for the first time and need it. And you have to prove it. And again, you proved it absolutely perfectly using as elementary, used exactly one thing. As Shang-Chi said, first day, expectation is a linear operator. You just used that fact and nothing else. And we're able to prove all of this nonsense together. And the rest of the homework is nothing other than this problem over and over and over again, collecting covariance terms and then writing out what those covariance terms are as a function of R0, R1, R2, VA, VD, and some other things. And these facts that you can take a sum, and the covariance of two sums looks like the sums of all the individual covariances, is what's going to make all of this stuff go down the road. And we're going to end up with hopefully some magical kind of looking results at the end. But does anybody have any questions about this? This is a nice, neat place to stop. Next time, we're going to prove the key results from Fisher 1918. That the resemblance between relatives can be broken down into their relatedness probabilities times various variance terms. And it's an incredibly powerful result. Questions about this? Okay, so I will see you guys Thursday, and we will finish up this homework.
Thank you.